Tim Pennings here. I'm going to start a series now of lectures on material which is traditionally covered in Calculus 2. I've have a whole series on Calculus 1, which I affectionately call Kitchen Calculus or Essentials of Calculus, which is found on YouTube. And now I'm going to cover the material in Calculus 2, which really is 4 different topics. The first is applications of integrals, which includes volumes of revolution and arc length and surfaces of revolution and work, I think, are the 4 that I'll be covering. And then the second topic is different methods of finding antiderivatives. There's a whole series of them. It's more interesting than methods of taking derivatives. That's pretty routine. It's kind of like long division. Multiplication is very routine, but back in the 5th grade when you did long division, especially long division with dividing by a 2-digit number, it suddenly became a little bit of guesswork. You had to kind of go off to the side and do a little trial and error. And that's kind of the difference between differentiation and integration. Differentiation is very routine. You learn the rules. Integration, there's a little bit of guesswork and creativity in being able to figure it out. Makes it a little more interesting, a little more mathematical, you might say. The third one is sequences and series, and there too, determining whether things converge or diverge. There's not a set of procedures. Instead, you have to try different things, and it becomes a little more creative, which makes it a whole lot of fun. I think it's my single favorite topic in calculus. And then the last thing will be some differential equations. So there it is, and we're going to get started today on the volumes of revolution. And unlike what I did in the first series, I'm not going to try to give what I consider the entire lecture that I would give in a class. Instead, I'll give kind of the essential things, and students or listeners can go to the book or just work out the rest on their own, which I will give everything that's essential. So let's begin with this question right here. Suppose you have some function, call it f of x, on the interval from a to b. And we know that if we want to find the area under that function, what do? We take all these little rectangles, and all those little rectangles have a certain height to them, f of x, and the width might be a little delta x right there, and then we sum them all up. And if you sum them all up, you're going to get something which is an approximation to the area underneath this rectangle. And the key is that as this width of the rectangle gets more and more narrow, then you're going to get a better and better approximation. So that in the limit, as you take the limit, as the length of those things goes to 0, you're going to get the true area. And in typical calculus fashion, as delta x goes to 0, it now becomes a dx, and this is going to be f of x. And I want something other than this summation, because this is the summation of discrete numbers of either a finite or infinite, but discrete, whereas this is going to be what happens when you push this all the way to 0. So we want a different notation. So we'll use an elongated s for sum, and we're adding all those things up from a to b, and that gives you the area under that region. Okay, so there's how we find and then of course what we learned in calculus 1 is that in order to actually evaluate it, all you need to do is to find an antiderivative of this function. So if this function, well, it doesn't look like anything I recognize, but you take an antiderivative of it, sometimes designated by capital F, and then you evaluate those at the endpoints, put it in for b, put in a, subtract take this one and subtract what happens when you stick in a, and you get the area under the curve. So super important and cool theorem there, the fundamental theorem. So that's that. So now we're going to ask a different question. I'm going to say, what volume would we get if we were to take this whole region here and revolve it around the x-axis. Now, I wish I had the props that my first grade teacher had. She had these things that you would pull out from her closet at various times of the year, Christmas, Valentine's Day, and so on. And it was 2 pieces of cardboard with kind of a mesh in between. And so they were hinged on one side, and she would unhinge it and pull them out like this, and then all this area became part of this kind of web honeycomb mesh. And so she had bells and she had circles, anything that was symmetric around this axis you could make. And so that's really what I need in order to illustrate this well. But this really requires some imagination on your part. Is you have to imagine you take this whole region, here's the axis right here, and we're taking it and it's hinged right there, and we're going all the way around and then back along the back side of the whiteboard, the other side, until you come back to where you began. So it's going to go all the way, there's half of it, and go on to the back side and then back up to where you began, and you're going to get a solid. What will that solid look like if you were to take this whole region? Given what I've drawn right here, it looks like it might be like a vase, right? Be a vase like this. If you were to take the vase and stick it up like this, it would be a vase that would look kind of like, well, that's not very good. Try it a little bit better. What's it gonna look like? It's gonna go something like that, right? Something like that, and there's the vase, okay? So, and the vase, of course, would be totally filled in. It's not a hollow vase, but it's something in the shape of a vase. So that's what you get. So the question is, how can we find the volume of that? And we're going to do the same sort of thing we did in finding the area underneath this thing. We're going to take a little sliver and we're going to ask, what's the volume that you're going to get by taking this little sliver all the way around, and we're going to add up all those little slivers. So let's assume that we're at some generic point x right there. So of course, if this is x, then the height of the function is f of x right there. Agreed? And so what's going to be the volume that you get by taking this little sliver, just this little sliver, all the way around back the other side? So can you see what it would look like? It'd be kind of, I went into the house and found something that looks kind of the same. It's going to be a very narrow little disc. Agreed? It's going to be a narrow disc. Here's like that, or here's the other thing I found. Okay, something more dear to my heart. It's going to be like this, all filled in, right? So that's why I like this one a little bit better. So there it is, right? Plus it gives me a little handle. Okay, so there it is right there. What would be the volume of this thing? Well, to get the volume of it, let's just first ask, what's the area of a circle? Okay, if you have a circle of radius r, then the area of that is pi r squared. Okay, why is the area of a circle pi r squared? Well, by definition, the circumference is 2 pi r, where this is in radians. So there's your circumference of a circle. let's just start at the very beginning. Pi is by definition the circumference of a circle divided by its diameter, and the diameter is twice the radius. So that's the definition of pi, and so the circumference of a circle is 2 pi r. Okay, so there's the circumference of a circle. So now if you have a circle and you take it and you slice it up into all these tiny little slices and pile them on top of each other, let's see once what we get. Whoops. You slice them and you stack them back and forth like this. If these are really small, this is going to effectively make a rectangle. And what's the area of that rectangle that you get by taking this whole circle and slicing it like that? Well, the length of each of these things is r. The distance all the way around is 2 pi r, which means that half the distance would be pi r. So that means here's half the distance, there's the other half the distance, because this is all of these make up the circumference when you add all those together. So you got half of it on each side, so this is pi r. And so now you've got yourself a rectangle, and the area of that rectangle is pi r times r, which is pi r squared. Okay? So the area is pi r squared. Okay? Pretty cool. I found that proof someplace, so it's kind of cool. So anyway, so there's the area of a circle. If it has radius r, then pi r squared is its area. And what we've got is something where this area is pi r squared, but then we have the third dimension is the thickness of it. If you're talking about volume, you're going to need 3 dimensions. Okay, you're going to need 3 dimensions for volume. So we've got 2 of them, pi r times r. R times r, it has dimensions of length squared. And now our third dimension is going to be this thickness. So you can think of it, if you want to, you can think of it as being a circle that's kind of laid on its side, and it goes up just a little bit like that. And so this right here is pi r squared. That's the base. And then you multiply that by a little tiny, let's call it a little, in this case, it's going to be a little tiny delta x. Okay, because there's the thickness. It's going to be a little kind of delta x. And so that's going to be the area of that little disk. Okay, so let's put this all together. So the volume of the disk is going to be this surface area. Okay, this surface area. In this case, the radius is going to be this height right there, right? That's the radius. That's you're coming all the way around like that. So the radius is going to be f of x. So here's your f of x squared. There's your radius pi r squared here. There's your radius squared times pi. That gives you this area. And now you multiply that by the thickness, which is a little delta x right there. And so that's going to give you a little bit of volume. That's going to give you a little bit of volume. Okay? And now you say, well, if that's the volume that you get by taking that little segment, then the total volume of taking this whole region out is going to be what you get by adding up all of those things as you go from A to B. And then, as before, we say, well, oh, I shouldn't say equal here. I should say approximately equal. Okay? But then you're going to get the true volume by taking, as before, the limit as those little delta x's get smaller and smaller and smaller. As you get thinner and thinner, you're going to get something closer to the true volume. So that's going to be the limit of this thing. And as before, that does what to it? It turns it into an integral. It's an integral of f of x squared times dx. The pi is a constant, so you can leave that inside or bring it outside. And you add all that up from A to B. So there it is right there. There's the volume. Of this region as you take it all the way around back up the other side. Okay? And so now, as I say, if I were teaching a class, I would now do 2 or 3 examples with various functions just to show how it works, but that's really the easy part. You choose anything you want. I mean, heck, I'm just too much of a sap here. I'm going to do one anyway. So here's f of x is equal to x squared. Let's say we want to go from 1 to 3. Okay? So we're going to take that whole region all the way around, and what are we going to get? It's going to be the volume is pi times the integral from 1 to 3. The function is x squared. Oops, I'm sorry, should have a squared there. X squared times dx, and that's going to be pi times the integral of x to the 4th dx from 1 to 3 pi. Antiderivative of that, of course, is 1/5 x to the 5th from 1 to 3, which is going to be what? Pi over 5. Put in a 3 here. Oh, wow. What's, I think that's 243. Minus 1 to the 5th is just 1. So there you go. Okay, there's your volume. It's really, really remarkable. Look how easy it is to find that the exact volume. Okay? So that's the way you do it. Now, as soon as I give you that one, you should be able to take the same idea to solve other kinds of examples. So for example, what if I wanted this region taken not around the x-axis, but taken around the line y equals -2. Let's make it -3. Okay, so and excuse me, it's this region right there. So going all the way down, you now are interested in this line here, y equals -3. You got this whole region here, and you're going to take that all around this line. Okay? What would the volume be? Well, just don't spend too much time saying, "Oh, I've got myself a formula. I'm going to use it." Instead, rethink what we did. Okay? Rethink what we did. What did we do? At any point x, what did we do? We needed this as our radius. In this case, the length of the radius is going to be f of x plus 3. Agreed? F of x is this length, 3 is this length, so f of x plus 3 is the entire radius. Same as before, you square the radius, you multiply it by pi, that gives you the surface area of this thing. And now you multiply it by the thickness, which is, I'm just going to go right to dx, a tiny little infinitesimal dx, and then you add them all up from A to B. And there you go. So there's your formula. So as I say, don't get caught up on the formulas. Instead, think through the process. Let me give you one more to do. Let's think about this one. What if you have two functions here? This is f, and say this is g. Right here. Okay? And we're interested in taking just this region around the x-axis. Okay, so it goes all the way around the x-axis, back up the other side. Now, do you agree that's going to be something hollow in the middle? Okay, you can stick your hand through the middle of it. It's going to be like a really strange angel food cake or something like that, right? Which has gotten, you took it out of the oven too fast and it started folding along the inside. Okay, I've made some like that in my years. Okay, so anyway, what's going to be the region for that? Now, if you're all obviously watching this on video, so take a moment and try to figure it out on your own before you watch me continuing, okay? If I were in class, I'd give them 2 or 3 minutes to see to try to figure it out on their own, and then we discuss it. So take advantage of it. Okay? Okay, I'm going to assume you did now, and I'm going to give you the answer. So here's what you should have thought. You should have thought, well, you might have been tempted to say this. If you were following formulas, you might say, well, let's see, I've got a g in there, and it might be f of x minus g of x quantity squared from A to B. Add all those up. That's just from having taught this 20 times or so, probably more. That's one answer that students often give. The other answer that they give as a possibility is they say, well, it's f of x squared minus g of x squared times pi from A to B. That's another one. Both of those, notice, are generalizations of this one. If g of x were equal to 0, Okay, if g of x were equal to 0, both of them would end up being this. So if you are looking at the formula and just trying to kind of guess from the formula, which isn't a bad thing to do, let me just make sure I'm still recording here. Okay, very good. I'm still recording. Either of those would be generalizations of this. Which one is correct and which one is incorrect? One of them is correct and one of them is incorrect. Can you tell the difference? Well, here's the way I think about it. I say, to get this region right here, the way to do it is to first find the volume of this whole big region going all the way around, which is pi times f of x quantity squared dx from a to b. That's everything, including this. And then I'm going to subtract this inner region. When I say the region, I'm going to say what I mean is subtract the volume generated by this lower inside region there. And so that's going to be pi times the integral from a to b of g of x squared dx. And I'm convinced that that's true, right? You take the larger one and then you hollow out the middle part and you're going to get the whole thing. And now you know from rules of integrals that if I have something like this, I can combine them together. They have the same limits of integration. I can factor the pi out front and I end up with this thing right there. So that is the correct answer. Why is this not the correct answer? Why doesn't that seem kind of reasonable? Why would that not be correct? You're taking, at some point x right here, you're taking f of x, which is its height, and then g of x is that height, and you're taking the difference between them. Why doesn't that work? And the reason to see why that doesn't work, I love it, asking this question in class, because you always get a couple students who see it, and that shows they really have a good understanding. The reason is that if you had this region right here, but instead of being this far up, instead it were way up here. Okay? Here's your f and here's your g, but instead of being only this far away from the x-axis, you're now this far away from the x-axis. Notice that f minus g is going to be the same thing in both cases. See that? This distance is the same as this. However, do you all agree that if I take this region all the way around, I'm going to get a much larger volume than taking this region around, because it's the same cross section here, but I'm taking it around a much larger radius, as it were, going around a much larger circle than this. And this doesn't take into account the fact that you want to know how high up you are. This is all that's interested in, is just what's the difference between those two functions. The difference is the same, but certainly the volume is going to be different. So there you go. So there's what I want to show you by way of oh no, I guess doggone it, as they say, I love to do examples. Let's see once how this is very practical in solving some things. Finding, for example, the volume of a cone. Okay, here you have a cone right here, which has height h and radius r, and you want to find the volume of that. How do you find the volume of it? Well, the hardest part, again, I know just from experience of calculus, is often not performing the calculus. It's just knowing all the things you need to bring into a calculus class, and also just using your imagination. You need to come up with some sort of a function that when I take it around the x-axis, I get myself a cone. The easiest one for me is just this one right here. There's a straight line, and I want this height to be h, so this is going to be h0 right here. I want the radius to be r, so this is going to be hr right there. And so that's the region I'm going to take all the way around the x-axis. Okay, that was the first bit of inspiration in order to solve the problem. The second thing you need to know is, how do you find the equation of that line? That's something that you probably learned back in 9th or 10th grade, okay? But you've forgotten it, and you have to know that stuff in order to do well in calculus. So what do we have? We have a line that goes through 0, 0, and through this point, the slope of the line is the rise over the run, r over h, so it's going to be just y is equal to r over h times x. Okay, and so there's the slope, there's your function, and now you can just plug it in here, and you get the volume is equal to pi times r over h times x, quantity squared, dx from 0 to h. There's your pi. You multiply this out, you're going to get an r squared and an h squared. Those are both constants, so I can bring those out front. And let's do a couple steps in one. I'm going to be left with an x squared there. The antiderivative of x squared is 1/3 x cubed. There's the antiderivative, and I evaluate that from 0 to h. And what do we end up with? We're going to end up with pi over 3. Takes care of that. I'm going to get r squared. Here, when I stick in an h, I'm going to get h cubed, but it's divided by h squared. It's just going to be h right there. And that's what happens when I stick in an h. If I stick in a 0, I get 0. So there's the answer right there. Okay? I'll leave one for you. Find the volume of a sphere. Okay? Go ahead and find the volume of the sphere. You need to first find the equation of a circle. Ah, heck. Let me get you started on it. This is my greatest weakness as a professor. I should just stop all the time, but instead I just love to explain things. So again, what do? We need ourselves a half circle, which I can take and go all the way around the x-axis. So what's the equation of a circle that has radius r? Well, what is true? If I want some point on this circle right here, x, y, what does that point have to satisfy in order to be on that circle? Pythagorean's theorem tells us this is x, this is y, so apparently x squared plus y squared has got to be equal to r squared. So there's the entire circle. The top half of it, if you solve it for y, is going to be the square root, the positive square root of r squared minus x squared. So there's your circle. So now what do? We want the volume is going to be pi times the integral. Well, watch. I can go from negative r to r and get this whole thing, but why not save a little time and just go from 0 to r and then double it, right? Use some symmetry there. So I'll double it, and then what do? I square this function. That's going to be easy. If I square it, I'm just going to get r squared minus x squared, and then dx. Look how easy that is. It's going to be 2 pi. Let's, again, I'm going to go through this stuff kind of fast, assuming that you know it. Or if you don't know it, you can turn this off and pause it and figure it out on your own. But the antiderivative of r squared, r is a constant, so it's just going to be r squared times x. Just like if this were a 5 here, it would be 5x. Okay, this is going to be 1/3 x cubed. Okay, from 0 to r. You stick in an r there, and you're going to get r cubed minus 1/3 r cubed, which is 2/3 r cubed. So it's going to be 2 pi times 2/3 r cubed, which of course gives 4/3 pi r cubed. There you go. So how cool is that? So there's the volume of a sphere. Okay, volume of a sphere. Okay, in the next lesson, we're going to learn the other neat method of finding solids of revolution. It's called I call it the cylinder method. So that's coming up.